For decades, cosmology relied on a remarkably successful assumption. Give the universe enough time, and complexity will emerge slowly. The first stars ignite, small galaxies assemble. Gravity pulls matter together over hundreds of millions, then billions of years. Large spiral galaxies, giant stellar populations, and supermassive black holes belong to a mature universe, not a newborn one. That picture was never a guess in the casual sense. It grew from decades of observations, simulations, and measurements that consistently pointed toward the same broad history. The earliest universe was expected to be simple, not empty, but unfinished. Then a new telescope opened its mirrors. The James Webb Space Telescope was designed to look farther into space than any optical observatory before it. Looking farther also means looking backward in time. Because light travels at a finite speed, every distant galaxy appears as it existed when that light began its journey. Webb was built to examine an era when the first generations of galaxies were just beginning to emerge, only a few 100 million years after the Big Bang. Astronomers expected surprises. Every major observatory has delivered them. What they did not expect was how quickly those surprises would arrive. Within its first observations, Webb began identifying galaxies that appeared unexpectedly bright, unexpectedly massive, and unexpectedly evolved for their age. Some candidates seemed to exist less than 400 million years after the beginning of cosmic history. Others displayed levels of organization and chemical enrichment that suggested substantial generations of stars had already formed and died. At first, the simplest explanation seemed obvious. Perhaps the distances were wrong. Estimating the age of an extremely distant galaxy is difficult. Initial measurements often rely on colors recorded through different infrared filters. Dust, unusual emission lines, or other astrophysical effects can imitate the appearance of a much dimmer object. Astronomers have seen mistaken identities before, and spectroscopy early excitement. Several early Webb candidates were later reassigned to much closer distances after more detailed observations. Ours that should have settled the matter. Instead, another pattern emerged. As spectroscopic confirmations accumulated, many of the most remarkable galaxies refused to disappear. Their exact properties became more precise, but the broader message remained. The early universe seemed capable of assembling luminous, substantial galaxies, faster than many pre-Webb models had anticipated. That distinction matters. Headlines often claimed that Webb had broken the Big Bang. Others insisted that modern cosmology had collapsed overnight. Neither description matched the evidence. The Big Bang itself was not under attack. The expansion of the universe, the cosmic microwave background, and the large-scale distribution of matter remained supported by extensive observations. The tension appeared somewhere more specific. The question was whether galaxies could grow this rapidly within the framework we already had, or whether some assumptions inside our models of galaxy formation required substantial revision. That may sound like a technical disagreement. It is anything but. Imagine opening a history book that states the first cities appeared around 5,000 years ago. Then archaeologists uncover a fully developed metropolis dating back 20,000 years. Human civilization would still exist. Earth would still orbit the sun. But nearly every explanation for how civilization developed would require another look. Webb presented astronomers with a comparable situation. The galaxies were not merely present. Some looked unexpectedly productive, converting gas stars with extraordinary efficiency. Others appeared surprisingly massive. A few hinted that supermassive black holes had already grown to astonishing sizes while the universe itself was still in its infancy. None of these observations automatically overturn established cosmology, but together they force an uncomfortable question. How did so much happen so soon? Springer 3. The answer is, it's not as simple as making gravity stronger. Galaxy formation is an intricate process involving dark matter halos, cooling gas, stellar feedback, radiation, chemical enrichment, and black hole growth. Each process influences the others. Adjust one assumption, and the consequences ripple through billions of years of cosmic evolution. That complexity creates both opportunity and uncertainty. Perhaps early stars were different from those forming today. If massive stars were more common in the young universe, galaxies could appear brighter, without containing as much mass as first estimated. Perhaps bursts of star formation occurred more violently than simulations predicted. Perhaps growing black holes contributed more infrared light than initially recognized. Or perhaps several modest corrections rather than one revolutionary idea eventually reconcile observation and theory. These remain active areas of research rather than settled conclusions. Arcs of yet one detail refuses to fade. Before Webb, these earliest epochs were largely invisible. Models filled the gaps because observations could not. Now the observations have arrived, and they are exposing places where confident expectations meet unfamiliar evidence. History shows that science rarely advances because everything falls apart. More often, it advances because reality refuses to fit comfortably inside assumptions that once seemed sufficient. The galaxies Webb has revealed are not frightening because they invalidate physics. So they are unsettling because they expose how much of our confidence depended on a universe we had not actually seen. For the first time, humanity is observing the opening chapters of cosmic history directly. And those first pages do not read quite the way we expected. One reason the Webb observations triggered so much debate is that astronomy has experienced false alarms before. New instruments almost always reveal objects that appear to contradict established theory. A few months later, calibration improves, additional measurements arrive, and many of the apparent anomalies disappear. That history shaped the scientific response. Instead of declaring a crisis, research groups began asking a narrower question. Which galaxies genuinely challenge existing models and which only appeared unusual because the earliest observations lacked complete information? The distinction matters because distance alone is difficult to measure across almost the entire observable universe. When Webb identifies a faint infrared source, astronomers first estimate its redshift. As the universe expands, light stretches toward longer wavelengths. The farther a galaxy lies from Earth, the more its light has shifted. Early estimates often rely on photometry, comparing brightness through different filters. It is an efficient method for finding candidates, but it is not the final word. Spectroscopy provides a stronger test. Instead of broad telescopes, spectroscopy separates light into thousands of individual wavelengths. Tiny emission and absorption features reveal the chemical elements inside a galaxy and allow its distance to be measured far more precisely. Several early Webb discoveries that generated dramatic headlines eventually turned out to be significantly closer than first believed. Those corrections were not failures. They demonstrated that the scientific process was working exactly as intended. What surprised researchers was what remained after those corrections. Even after removing the mistaken candidates, enough confirmed galaxies continued to occupy an uncomfortable part of the timeline. Some possessed stellar masses that theoretical simulations struggled to reproduce only a few 100 million years after the Big Bang. Others appeared to have converted gas into stars with remarkable efficiency. None of these galaxies violated physics. They challenged expectations. That difference is easy to overlook outside the scientific community. Modern cosmology does not predict the position of every individual galaxy. It predicts statistical populations. Simulations begin shortly after the Big Bang, evolve dark matter under gravity, model gas cooling, star formation, supernova explosions, black hole growth, and countless other processes. If those simulations consistently produce far fewer massive galaxies than Webb observes, then one or more assumptions inside the model deserves another look. Notice what has not changed. Gravity still behaves as general relativity predicts across enormous scales. The cosmic microwave background continues to match observations with remarkable precision. Measurements of primordial chemical abundance still support the broad picture of a hot, dense, early universe. The tension exists between those successful foundations and the complicated physics that transforms simple matter into mature galaxies. That leaves astronomers with several possibilities. One possibility is that the earliest stars differed substantially from those forming today. The first generation of stars emerged from almost pure hydrogen and helium, without heavier elements to cool collapsing gas clouds. These stars may have grown much larger than typical modern stars. Larger stars burn brighter, evolve more quickly, and enrich their surroundings with heavier elements after explosive deaths. If these processes occurred more efficiently than many models assumed, early galaxies could appear brighter without requiring extraordinary amounts of mass. Another possibility concerns dust. Dust is often treated as an obstacle because it absorbs visible light. Yet in the infrared, dust can also reshape how galaxies appear. Small uncertainties in dust composition or distribution may influence estimates of stellar mass, age, and star formation history. Black holes introduce another complication. Webb has detected evidence that some galaxies already hosted actively growing black holes, surprisingly early in cosmic history. Material falling toward a black hole releases enormous amounts of energy. If part of the observed infrared light comes from an active galactic nucleus rather than stars alone, estimates of a galaxy's stellar population may require adjustment. Even so, these corrections do not eliminate every discrepancy. The remaining observations continue pointing toward a universe that may have assembled complex structures faster than expected. That possibility reaches beyond astronomy. Cosmological simulations influence our understanding of chemical, evolution, planetary formation, and even the environments where life could eventually emerge. Change the timing of galaxy formation, and countless downstream assumptions require careful examination. It resembles discovering that the first chapter of a long novel began decades earlier than previously believed. Every later chapter still exists. Every character still appears. But the relationships between them suddenly acquire a different meaning. For years, cosmologists assumed they were reading the opening pages correctly because the ending fit remarkably well. Webb has provided access to those opening pages directly. They are familiar enough to recognize, yet different enough to suggest that some early events unfolded on a faster schedule than expected. The uncomfortable implication is not that our theories have failed. It is that they may have succeeded partly because the universe kept one of its most important periods hidden until now. As new observations continue, astronomers are no longer asking only what existed shortly after the Big Bang. They are beginning to ask whether the universe became recognizable far earlier than anyone had imagined. That question reaches beyond the first galaxies. It reaches into the assumptions beneath nearly every simulation of cosmic history. Long before the James Webb Space Telescope ever launched, cosmologists understood that building a galaxy was never simply a matter of waiting. Gravity begins the process, but gravity alone cannot explain what we observe. Shortly after the Big Bang, ordinary matter was spread with extraordinary uniformity. Tiny fluctuations in density, preserved in the cosmic microwave background, acted as seeds. Regions containing slightly more matter exerted slightly stronger gravitational pull. Over millions of years, those regions attract additional material, eventually becoming the invisible scaffolding known as dark matter halos. Everything visible followed that hidden architecture. Gas cooled inside these halos. The first stars ignited. Their radiation altered the surrounding environment. Their explosions scattered heavier elements that later generations of stars would incorporate. Every galaxy became the accumulated result of countless interactions, each affecting the next. It was never expected to happen instantly. In fact, many of the processes that make galaxies efficient also slow them down. Massive stars emit enormous amounts of ultraviolet radiation. Supernova explosions launch shockwaves capable of driving gas completely out of small galaxies. Black holes, once active, can release enough energy to suppress further star formation. These feedback mechanisms prevent galaxies from converting all their available gas into stars at once. For years, simulations suggested this regulation was essential. Without it, the nearby universe would contain galaxies far brighter and more massive than astronomers actually observe today. That creates an unexpected tension. If feedback limits growth in the modern universe, why do some galaxies in the early universe appear to have expanded so rapidly? One possibility is that the earliest conditions favored unusually efficient star formation. The universe was denser then. Gas clouds collided more frequently. Matter flowed continuously into young dark matter halos. Under those circumstances, galaxies may have experienced bursts of activity far more intense than those typically seen today. Computer simulations have begun exploring exactly this possibility. Some newer models reproduce Webb's observations more successfully by allowing gas to cool faster, by increasing the rate at which stars form under early conditions, or by adjusting how stellar feedback behaves inside primitive galaxies. None of these modifications require abandoning modern cosmology. Instead, they acknowledge that the earliest universe may have operated under environmental conditions unlike anything common in the present era. Even so, another puzzle remains. Brightness is not the same as mass. When astronomers estimate the mass of a distant galaxy, they are interpreting light that has traveled for more than 13 billion years. That light contains clues, but never direct measurements of every individual star. Suppose two cities are viewed from orbit at night. One contains millions of small homes. The other contains fewer buildings. But every structure is illuminated by powerful floodlights. From space, the brighter city might appear larger despite containing fewer people. Astronomers face a similar problem. If early galaxies contained unusually large, short-lived stars, they could produce enormous amounts of light without requiring as much total mass as originally estimated. A small change in the stellar population can significantly influence how observers interpret an entire galaxy. That possibility has become one of the most active areas of research. The first generation of stars, often called population 3-star stars, has never been observed directly. They are believed to have formed from nearly pristine hydrogen and helium before heavier elements existed in meaningful quantities. Theoretical studies suggest these stars may have reached masses hundreds of times greater than the Sun before ending their lives in spectacular explosions or direct collapse into black holes. If Webb is indirectly seeing environments shaped by descendants of these primordial stars, then some apparent anomalies may reflect unfamiliar stellar populations rather than impossible galaxies. Yet every solution seems to introduce another question. Large stars die quickly. If they dominated the earliest universe, they should also have enriched surrounding gas with heavier elements at remarkable speed. Webb has indeed detected chemical signatures indicating that some surprisingly distant galaxies were already more chemically mature than expected. Again, the evidence points in the same direction. Something in the opening era of galaxy formation appears to have unfolded with unexpected efficiency. That efficiency may also explain another mystery emerging from Webb's observations. Several extremely distant galaxies appear surprisingly compact. Instead of sprawling structures resembling the Milky Way, they pack enormous luminosity into remarkably small regions. Gravity alone can produce dense systems, but maintaining such rapid growth while regulating stellar explosions remains difficult to reproduce consistently across simulations. The challenge resembles reconstructing the early years of a civilization after discovering that major cities, advanced metallurgy, and complex governments all appeared within the same unexpectedly brief historical window. Each individual achievement might be explainable, but the combination becomes harder to ignore. This is why cosmologists are resisting dramatic conclusions while simultaneously taking the data seriously. The observations are not isolated curiosities. Together they form a pattern. Patterns carry more weight than individual anomalies because they suggest that separate measurements may share a common cause. Whether that cause lies in star formation, dark matter behavior, black hole growth, observational bias, or a combination of all four remains unresolved. What has already changed is the direction of the investigation. Only a few years ago, researchers spent much of their effort predicting what Webb might find. Now Webb is determining which predictions deserve to survive. The telescope has not delivered a replacement for modern cosmology. It has done something that science values even more. It has exposed exactly where certainty becomes assumption, and history suggests that those boundaries are where the deepest discoveries usually begin. As the list of unusual galaxies continued to grow, another possibility became difficult to ignore. Perhaps the problem was never the galaxies themselves. Perhaps the simulations had been too confident. Modern cosmology depends heavily on numerical models because the universe is too large and too slow for direct experiments. Researchers construct virtual universes inside supercomputers, beginning with conditions measured from the cosmic microwave background. Gravity pulls matter together. Gas cools, stars ignite, black holes grow, galaxies merge. Billions of years pass in a matter of weeks of computation. The remarkable part is how well these simulations usually work. Projects such as Illustrist, TNG, and Simba reproduce many properties of the nearby universe with impressive accuracy. They generate galaxies whose sizes, distributions, and chemical compositions resemble what astronomers observe today. That success gave researchers confidence that the underlying physical assumptions were correct, but matching the present does not guarantee every stage of the past. A simulation is only as reliable as the ingredients it includes. Some processes occur on scales too small to calculate directly. The birth of individual stars, the turbulence inside molecular clouds, and the behavior of supernova explosions happen far below the resolution of even the largest cosmological simulations. Instead, scientists use carefully tested approximations known as subgrid physics. Those approximations are not arbitrary. They are built from observations and smaller-scale calculations, yet they remain approximations. If one of them behaves differently under the extreme conditions of the early universe, small differences can accumulate over hundreds of millions of years until the simulated universe begins to diverge from the real one. That possibility has become increasingly attractive because it requires the fewest extraordinary assumptions. Rather than rewriting gravity or discarding the Big Bang model, researchers ask whether young galaxies converted gas into stars more efficiently, whether feedback temporarily weakened under primordial conditions, or whether streams of cold gas supplied fuel faster than expected. Each adjustment sounds modest. Together they could reshape the first billions of cosmic history. There is another reason for caution. Astronomers are not observing every early galaxy. They are observing the brightest examples that current instruments can detect. This creates what statisticians call a selection effect. Imagine surveying the tallest buildings in an unfamiliar country while flying overhead. From that perspective, it might appear that every city consists entirely of skyscrapers. The smaller buildings remain hidden, not because they are absent, but because they fall below the limits of observation. Webb is extraordinarily powerful, but it still has limits. Its deepest observations naturally favor luminous objects. If the earliest universe contained a small population of exceptionally bright galaxies, surrounded by countless faint ones, our initial picture could become distorted simply because the brightest objects reveal themselves first. Researchers are actively correcting for this possibility. As Webb spends more time observing the same regions of sky, increasingly faint galaxies emerge from the background. Each additional detection helps refine estimates of how common these massive early systems truly are. The answer matters enormously. If the brightest galaxies are exceptionally rare, existing theories may require only modest adjustments. If they are common, then something more fundamental may be happening. This uncertainty illustrates an often overlooked feature of scientific progress. Public attention usually focuses on discoveries. Scientists spend much of their time measuring confidence. Every observation carries uncertainties arising from instrumentation, calibration, statistical sampling, and interpretation. The goal is not simply to find surprising results. It is to determine whether those results survive repeated attempts to explain them away. Many already have. The debate has therefore shifted. Instead of asking whether Webb found unusually mature galaxies, researchers increasingly ask why those galaxies formed so quickly. That subtle change marks an important milestone. The existence of the tension is becoming more secure even as its explanation remains uncertain. History offers several examples of similar moments. The orbit of Mercury eventually contributed to general relativity after resisting explanation through Newtonian mechanics alone. The accelerated expansion of the universe emerged only after repeated observations refused to fit existing expectations. In both cases, the anomaly did not immediately overthrow accepted theory. It identified precisely where further investigation was needed. Webb may be creating a similar moment, not because it has disproved decades of cosmology, because it has revealed where our confidence was supported more by successful extrapolation than by direct observation. For generations, astronomers reconstructed the universe's earliest chapters from the evidence left billions of years later. Now those early chapters are becoming visible themselves. They are not unreadable. They are simply more complicated than anticipated. And that complication reaches beyond galaxy formation. Because if mature galaxies appeared sooner than expected, another question naturally follows. What else might have developed earlier than our models predicted? The first heavy elements. The first planetary systems. Perhaps even the first environments capable of supporting chemistry far more intricate than anyone once imagined. The telescope was built to observe ancient light. Instead, it may also be forcing us to reconsider how quickly the universe learned to build complexity from simplicity. That possibility extends far beyond the galaxies themselves. It reaches toward every later chapter in the history of the cosmos, including our own. By now, the conversation has expanded well beyond a handful of distant galaxies. The deeper question is whether Webb is revealing an unusual corner of the universe or exposing a limitation in how we have imagined the universe's earliest history. That distinction affects far more than cosmology. Every planet, every ocean, every carbon atom inside every living organism traces its origin to stars. If stars formed earlier and more efficiently than expected, then the timeline for chemical evolution also shifts. The first stars contained almost nothing except hydrogen and helium. Everything else had to be manufactured: carbon, oxygen, silicon, iron, calcium. Every heavier element emerged inside stellar interiors or during the violent deaths of massive stars. Before those elements existed, rocky planets could not exist. Water-rich worlds could not exist. Biology, at least as we understand it, had no foundation. For decades, astronomers believed there was a substantial delay between the birth of the first stars and the appearance of chemically enriched galaxies capable of producing more familiar planetary systems. Webb suggests that this transition may have happened with surprising speed. Several confirmed early galaxies already show evidence that previous generations of stars had lived and died. Heavy elements had begun accumulating while the universe was still remarkably young. That does not mean Earth-like planets immediately appeared everywhere. It does mean the raw materials for complexity may have spread sooner than many models anticipated. Time, in cosmology, is often the most valuable resource. Every additional 100 million years allows gravity to assemble larger structures, stars to manufacture more elements, and planetary systems to emerge in greater numbers. If those processes began earlier, the implications ripple across cosmic history. Consider the search for life. Astrobiology does not begin by asking where life exists. It begins by asking when life could first become possible. The earliest universe was hostile. Radiation flooded space. Heavy elements were scarce. Stable planetary systems were unlikely. Eventually, those conditions changed. The question has always been how quickly. If galaxies matured faster than expected, then habitable environments may also have appeared earlier. Not necessarily abundant, not necessarily inhabited, simply available. That subtle distinction matters. The Drake equation, despite its uncertainties, treats the emergence of technological civilizations as a sequence of probabilities unfolding over time. Shift the beginning of that timeline, even modestly, and the statistical landscape changes. Civilizations, if they exist elsewhere, would have had more time to emerge, more time to develop, more time to disappear. Ironically, a universe that becomes complex earlier does not necessarily make the Fermi Paradox easier to resolve. It may deepen it. If suitable environments arose hundreds of millions of years sooner than expected, then intelligent civilizations, assuming they occasionally emerge, would possess even greater temporal advantages over humanity. The silence would become harder to dismiss as a consequence of insufficient time. Of course, this reasoning depends on many uncertain assumptions. Life may be extraordinarily rare. Intelligence may be rarer still. Technological civilizations may remain brief, or entirely different constraints dominate the equation. Webb does not answer any of these questions. What it does is redefine one of the boundary conditions. The universe may have become capable of supporting complexity sooner than we believed. That realization reaches into another field as well: black hole formation. One of Webb's most intriguing discoveries involves evidence for surprisingly massive black holes in extremely distant galaxies. Some appear to contain central black holes weighing millions of times the mass of the Sun, less than 1 billion years after the Big Bang. Growing objects of that size is not impossible. It is difficult. Black holes increase their mass by consuming surrounding material or merging with other black holes. Both processes require time. If enormous black holes already existed during the universe's youth, researchers must explain how they accumulated so much mass so quickly. Several possibilities remain under investigation. Perhaps the original black hole seeds were already unusually massive, formed through the direct collapse of enormous gas clouds instead of ordinary stellar remnants. Perhaps gas flowed inward more efficiently than simulations assumed. Perhaps repeated mergers accelerated growth. Or perhaps several mechanisms operated simultaneously during conditions unique to the early universe. None of these explanations has yet emerged as definitive. What matters is the broader pattern. Galaxies appear unexpectedly mature. Chemical enrichment appears unexpectedly advanced. Black holes appear unexpectedly large. Individually, each puzzle might be accommodated through careful revisions. Collectively, they suggest that the opening stages of cosmic evolution deserve far closer examination than anyone anticipated before Webb began observing. The telescope has become something more than a powerful observatory. It has become a test of intellectual humility. For generations, astronomers built elegant models using incomplete evidence because no better evidence existed. Now better evidence is arriving. The proper response is neither blind confidence nor dramatic rejection. It is the willingness to let observation decide which assumptions survive. That process can be uncomfortable. Not because it destroys knowledge, because it reminds us that knowledge is always provisional, even when supported by decades of success. The universe has not changed since Webb unfolded beyond Earth's orbit. Only our ability to see it has. And history repeatedly shows that every improvement in vision forces humanity to reconsider how much of reality remained hidden simply because we lacked the instruments to notice it. There is a temptation that follows every scientific surprise. If observations challenge expectations, people often assume two choices remain. Either the old theory survives untouched, or it collapses completely. Reality is rarely that dramatic. The history of science is filled with examples where the deepest progress came from something quieter. A successful theory remained largely intact, while the assumptions surrounding it became sharper, narrower, and more accurate. That may be where cosmology stands today. The James Webb Space Telescope has not delivered evidence that the Big Bang never happened. It has not shown that gravity suddenly behaves differently across the observable universe. It has not demonstrated that dark matter does not exist or that modern cosmology has failed. Instead, it has done something more valuable. It has revealed where our confidence exceeded our evidence. For generations, the earliest few hundred million years of cosmic history existed mostly inside simulations. Those simulations were built from excellent physics, careful observations, and decades of refinement. Yet they still depended on assumptions about processes that no telescope had ever directly observed. Webb crossed that boundary. For the first time, humanity is no longer reconstructing the opening chapters of the universe almost entirely from later consequences. We are beginning to read those chapters themselves. Some pages match remarkably well. Others contain details we did not expect. That is exactly where science becomes most productive. Every new spectrum, every confirmed redshift, every additional deep survey reduces the space available for comfortable assumptions. Researchers are already revising models of star formation, improving simulations of dark matter halos, refining estimates of black hole growth, and expanding observations into regions of the sky that have never before been explored at these wavelengths. Many of today's apparent tensions may eventually find entirely conventional explanations. Some may disappear as larger samples become available. Others may remain, forcing more substantial revisions. No one knows which outcome will prevail. That uncertainty is not a weakness. It is the reason astronomy continues to advance. There is another implication that reaches beyond equations and simulations. For centuries, every increase in observational power has altered humanity's place in the universe. Galileo revealed moons orbiting another planet. Hubble demonstrated that the Milky Way was only one galaxy among countless others. Measurements of cosmic expansion transformed the universe from something static into something evolving. The discovery of the cosmic microwave background allowed us to glimpse the universe in its infancy. Each instrument expanded not only our knowledge, but also our awareness of how incomplete previous pictures had been. Webb belongs to that tradition, not because it has answered the largest questions, because it has made those questions larger. If galaxies assembled sooner than expected, then the first generations of stars may have transformed their surroundings with astonishing speed. If heavy elements appeared earlier, then rocky worlds may have become possible earlier. If black holes grew faster, then the engine driving galaxy evolution may have begun operating almost immediately after the first structures emerged. Every answer extends the timeline of complexity deeper into cosmic history, and every extension forces another question. How much happened before believed the universe was ready? That question reaches far beyond astronomy. Human beings naturally imagine history as a gradual climb from simplicity toward complexity. The universe may not always follow that intuition. Under the right physical conditions, complexity can emerge with remarkable speed. Once gravity gathers enough matter, once the first stars ignite, once heavy elements begin circulating through space, the pace of change may accelerate far beyond what earlier generations of astronomers considered likely. The uncomfortable possibility is not that the universe is stranger than our theories. It is that the universe became recognizable long before we arrived to witness it. By the time light from those distant galaxies began its journey toward Earth, our sun did not exist. Neither did our planet. No oceans reflected sunlight. No atmosphere carried the chemistry of life. No species wondered where it came from. Those galaxies were already evolving while the future Earth remained nothing more than atoms scattered across interstellar space. Their light crossed more than 13 billion years before reaching a telescope, positioned 1 million miles from our world. Only now do we finally receive the message. Not a deliberate signal. Not evidence of another civilization. Something quieter. A record. A record showing that the universe's earliest history may have unfolded with greater speed, greater efficiency, and greater complexity than we imagine while looking from the safety of the present. That realization carries its own form of existential weight. Every generation believes it has inherited a clearer picture of reality than the one before. Every new instrument eventually proves otherwise. The James Webb Space Telescope has not ended one story. It has exposed the opening pages of another. And if those first pages already contain surprises, then the most unsettling possibility is not that we misunderstood the universe. It is that we have only just begun to observe the period where its deepest assumptions were written.